for being here again. So the title of my talk and slash demo is Spark, using Spark for large-scale experimentation plus switching to using Spark itself for training on the big data mode with its own machine learning library. So I'm actually very excited for this demo, for this talk, because we're switching a bit to the cluster side. It's my favorite part. In the previous presentations where it was more like one node talking to the other, that's all interesting, but this is more interesting. Quick intros here, quick bio. I'll explain a bit what it means about doing why having different modes of machine learning and what each one is supposed to do. Each one is good for what. Quick intro to Spark and a quick tour of web user interfaces so that you guys are familiar with just a bit cluster side and user interface that you can monitor the Spark cluster and the things around it. Second section is the large-scale experimentation with Spark. So that is the part that I'll take a minute just in following the slides to explain. So this is basically using Spark as a distribution engine, a generic distributed processing, so that you can distribute training of a machine learning model, which is it's a single machine library. So it can be scikit-learn, or it can be, in our case, it's a stats model, which has the model that we are interested in. But it could be scikit-learn, it could be any number of other libraries that are just built to run on a single machine. So we are using Spark to distribute it over a cluster so that we can go faster, basically. So that's the second part. The third part is on the machine learning on big data. So let's say this is the more traditional use of Spark, using Spark's own machine learning library, ingesting big data, and training the model, exporting it, and then serving it with MLeap, which is a production quality, low latency serving engine. So I'll try to go a lot of things this evening, and there's a lot of code, but I'm gonna, for the most part, skip over the bulk of the code, but I'll show you the key parts that make the magic happen, if you will. But we're not gonna have time to go line by line today. Quick bio, my experience has been in data science, so a variety of data science projects on big data applications, distributed algorithm design on a Hadoop platform on Spark, data mining, deep learning, a couple of big projects on deep learning, especially on TensorFlow implementation, transport mode detection from telematics data, problem detection out of images, cracked equipment on convolutional nets. So I've covered a wide spectrum of data science projects, and that kind of experience in the past several years has been distilled into our own platform, Unaltka, which is built from scratch. So it has the components that basically I've been using, and I'm using the same platform today for our demo. So this is borrowing one slide out of our own presentation of the platform, because it kind of depicts nicely what we are talking about here. So just before I forget, the Spark that we have, so there's a Spark master that is running on master 1. And there are two executors, Spark and then Spark here. So these could be like CPU machines. It's a CPU library, so it's not using GPUs. So there are two executors running on each of these workers, and that is our Spark cluster for the demo. Back to the machine learning part. So just quickly give you an idea of, when you want to use which of these modes of machine learning and why. So the first one, let's say, and we are interested in, on this slide, the number 1, and I'll mention number 2 specifically, and I'll mention the others just briefly. So number 1 is the Horovod and TensorFlow. So this is when you have basically big data, and it doesn't fit in the system memory of a single machine, so you distribute it over a cluster. And that is the model that we call data parallelism. So each machine holds a part of this data, and each worker, each TensorFlow engine basically trains on its own portion. And Horovod has an implementation of an algorithm called ring-gauge reduce, which is basically a circular exchange of updated gradients so that altogether they converge to a single trained model. So each worker basically sees part of the data, and then they train and they exchange updates to gradients. So Horovod, TensorFlow, Horovod is out of Uber. They have a very large and advanced data science team there. And that is not what we're using here today. But this is available as an open source project. I highly recommend it if you want. And just while we are on this subject, at the bottom I put some additional pointers, and the lower one, Legacy 2016, is what I actually contributed to. It was a project called Tensor Spark. And I worked on productionizing it in Yarn cluster mode, so that basically what these guys behind this product developed, I worked on it so that it could talk to Yarn, so you could actually run it in a production Hadoop cluster. But that is, in machine learning times, that is basically Stone Age, I guess, 2016, so that is no longer relevant. What I would recommend right now is Horovod. So that is, if you have a large data set, you want to use Horovod. And Horovod talks to TensorFlow, but it also uses actually other libraries, like it can work with PyTorch, MXNet, a few others. So it is actually not tied to TensorFlow either. Number two is the Spark. So using Spark as a distributed, generic distributed engine, so that you can use scikit-learn or anything else to distribute the processing. And that is what is the second item on my outline. That is, I'm going to explain. The third item here, RayTune, is when you want to go a bit more sophisticated than a grid search. The state of the art is hyperband, which is outperforming Bayesian optimization, random search, and of course grid search. So if you want to do a bit more sophisticated than grid search, I would highly recommend that you look at RayTune. And specifically, Ray is a Ray cluster, so it's a lightweight Spark cluster, think of it, but it's very lightweight compared to Spark. Specifically, it has already an implementation of hyperband, so that's why we've gone with this one, so we don't have to do it ourselves. So there's a trade-off between number 2 and 3 in terms of ease of use. I would say I still like 2, using Spark as a distributed engine. But then there's also RayTune, which is a bit harder to operate and interpret the results, so a bit harder to use, let's say. But that is an option available. And additional pointers I've put, and I haven't mentioned here, that's why I've added those additional pointers. Like, of course, the first point is the using Spark as a big data library, just using its own library. And that is what I'm going to show on the third section of this presentation. So just a quick introduction to what Spark is. It has many APIs. You can talk to it in several languages. Python is what we're using. It has machine learning library, streaming, SQL, graph. So it is a very advanced cluster technology that it has integration with many. It has already, embedded and has implementations for many algorithms. So I would really recommend for you to use it. Zeppelin, that is, you're going to see, is a notebook, which is equivalent basically to Jupyter Notebook. So on the cluster world, usually people tend to go with Zeppelin, and that's what we are using it. But you could do pretty much the same thing with Jupyter as well. But with cluster side, the Zeppelin has a better integration, and you'll see a bit why. So just the terminology, we say Zeppelin note, which is equivalent to a Jupyter Notebook. We have a Zeppelin paragraph, which is equivalent to Jupyter cell. So each of these that you see boxes basically is a paragraph, is a Zeppelin paragraph. And for each, you can actually decide what the interpreter is. For example, here is the interpreter sh, which is the shell. So we're executing basically a shell command here. But it supports, for example, Python, PySQL, the SQL interface to Spark, and dozens more interpreters. So basically, the advantage is that within a single Zeppelin node, you can change interpreter from one paragraph to the next. And in the case of Spark, the good thing is that you can pass variables between, work on it a bit on Python, change it to SQL, work on SQL, pass it, maybe write something on Scala because somebody has written it in Scala already, you want to copy, use that. So it's good to switch back and forth languages while you're still within Spark, and then you can use Zeppelin for that. So that's and also, last point is, with Zeppelin is that it has also integration with Git, and we have a Git server on the cluster, our own cluster, on master 2, which is basically connected to this. So it would give a good version control, but it's a very nice version control. If I have time, I can show you this as well. So it is it's good integration with this. By the way, I've put this screenshots here just so that the deck is a bit more complete, but I have all these opened in my browser. So if you have questions, feel free at the end. By the way, I'll take questions at the end, and I can show you more the interface, how it's working if you wish. So this is Spark master. This is Spark cluster. So as you see, there are 2 workers that I just mentioned at the beginning. Each of them, we have given 6 cores out of the 8, so that each worker, each executor is using 6 out of 8. We've given about half of the memory to each executor here. So that is the resource allocation for this. And when Zeppelin launches the Spark application, it's going to be basically a long-running Zeppelin application. And then whatever you submit, it becomes a job within that. This is just a quick view on the Spark application itself. So this, and I'll get to this, and I'll explain a bit more what this is. But the part that I just want to show you here is that we had 12 cores total for the Spark. So 6 cores out of each worker, 12 cores. And when you launch a job, Spark behind the scenes basically manages these 6 on each executor, 6 tasks on each executor. So it runs 6 tasks simultaneously on each machine. And that is what you see. Because what the job that I've launched is basically going to use all the resources. So it launches 6 tasks per core, per machine. And that is when it's complete, and that is the job that has been completed. So these are all the 12 tasks. You can see, for example, they are running on executor 1, 0, 1, 0, 1, and then the duration of each. So that is if you want to monitor how the processing goes, that's where you want to come. This is a view of our HDFS, and so we are using Hue to navigate through HDFS. The part that is going to come up on the 3rd section of this presentation is it's a data set of Airbnb listings. So this is the data set that we are going to ingest, and when the training is done, we're going to export the model, and it's going to sit here. So these 2 files are basically what they're going to be generated in this 3rd section. I'm just showing right away what they look like. And that is our Git server with GitLab, which is running a master tool, which is connected to Zeppelin. And these are the Zeppelin nodes here that each one is connected. So it's basically as a tight integration, and it makes life easier, actually much easier than Jupyter. Doing Git control of the Jupyter is not very straightforward still. There's some packages extra that you can do a bit more, but I don't think it's in my view at least, it's not as nice as Zeppelin. So the second part, I'm going to walk you through a Zeppelin node. So this is basically training a ARIMA model, which is autoregressive integrated moving average. It's a widely used model in the time series production. So and from the stats model, it's a Python library. So we are using that in this Zeppelin node. We train it with distributed training, and once that is done, it's going to just save the results in a in a CSV file that holds all the experiments and the error that has been calculated. And then we're just going to use a Jupyter Notebook to process that. And that's the part that I'm going to show you, that parallel coordinates visualization and how to interpret that. And you see the points when I get there. And a third Jupyter Notebook just to show you what the predictions look like. Basically, when we pick up one parameter and making prediction, how does that work? This you'll see this in a bit. So this is a parallel coordinates visualization. So this is the first Zeppelin node, which is going to launch our grid search. So we are managing basically the way this is done on the application layer. Basically, the way this is distributed, we are managing it all here in this application that we are writing. The application, the Spark application. So here I'm using, like basically I've coded, like I've put 3 flags that you can run it as a Spark distributed single core, or it could be a local Python, or it could be multi-core. And the difference between single core and multi-core is that if you have a library that is gonna only use one core out of your machine, then that's the way you want to use, that's the flag you want to use, and I'll show you at the bottom what that does. But then if you have a library that already uses all the cores, you just want to distribute over the machines, and you don't want Spark to then go distribute it within the cores of each machine. You don't want to do that. You set the flag to multi-core, and it has a different implementation. It's here, but I won't have time to get to it. But that's the interesting part. I think it's more interesting. That's why I'm showing it. This is when some libraries, including what I'm using actually here, Arima, are for the most part single core. So you get a huge benefit when you use this paradigm of implementation, when you parallelize it with Spark. So Arima itself, the part that I'm going to show you. So just quickly on Arima. Arima has 3 main parameters: PQ, PDQ. P is controlling the basically autoregressive part, the regression, the number of lag observations that is like keeping track. So P value, if it's actually 6, between 1 and 6, this library behaves like a single core library. But if you set the P to 7 and higher, it's actually multi-core on the machine. So they have some like an implementation decision they have made on the library that apparently has a threshold on this parameter. So here we are using 1 to 5, and it's going to fall into kind of like single core Arima. And then D is a difference just to make the time series semi-stationary. Q is another variable for the controlling moving average, and we have control over solver, max iteration. So we are basically iterating over 5 parameters, and this combination. So for each one, let's say P that we have here, we set it 1 to 5, and then all these combinations we have 450. And actually, I can run this. This is going to take about 9 minutes on this cluster to run. So the last part, I'm going to let it run. So this is going to run on this cluster, and it's going to turn out the results in about 9 minutes. So we'll let this run. And if I have time, I can show you there, but there's not much interesting happening. So it just saves the results. This is the one that I'm going to use for the parallel coordinates visualization. So this one I'm using like a much larger values, more values per parameter. And this comes about like 12,000 experiments. So this is like you want to explore 12,000 experiments on 5 dimensions. And that is why I'm going to use parallel coordinates to make sense of what's coming out. That's the point of this. I'm not going to run that, of course, because it's going to take some time. This is broadcasting the variable, so we're reading the data set, we're shooting it to the executors with this command, so that each executor has a has the data. There's the function train ARIMA that is basically training on this. So it picks up the parameter values and trains it. And the measure of error that we have is basically, the model is basically training on history and is making one bar at a time prediction for the following 30 days. So think of it as a sliding window. So it's training, let's say, on the past 30 days, it makes a prediction for tomorrow, and then it adds tomorrow to history, retrains it, makes a prediction for the day after. So it's a moving prediction. And then we just, so we have 30 days of predictions, we have 30 days of actual values, we just calculate an error on the prediction. So it's a basically mean squared error of the prediction. That's the error metric. Run experiment is a function that is basically, for the most part, it just calls that function that we defined above. So it's just a wrapper that we don't put everything here. It launches, it passes each experiment's details to this ARIMA function, and at the end it's saving the result. Here, this is because it's running, it's a bit grayed out. And if I show you actually the running as, and this is what is running right now, and so these are the 12 tasks. So it's running like about 2.5 minutes each, and then it's going to jump to 9 and it finishes. So that is a view, but then just so that I can use, this is now a bit grayed out, so I use another notebook. So that's going to run and it's going to finish on its own. I'm going to just, so this is the 12,000 experiments that are here that I had run actually over the weekend. So the part that I'm going to just show you here is the single core case. And so when the execution mode is single core, it basically, what we do is that we create a Spark data frame which holds each experiment's details. So all those combinations we had, it has the experiment details, so one record for each experiment. And then we define a UDF, user-defined function, which basically calls that run experiment function on each record. So what that gives us is that Spark itself is going to distribute the executions over the cluster. You don't have to worry about anything else. It's going to schedule all the tasks, all the experiments over the cluster, and it's going to basically run its, let's say, think of it as a queue over each core, and then so it's going to sequentially empty this queue, and it's going to schedule when one is done, it passes to the next experiment. So it's going to manage the resources of the cluster. So that is the logic. And when that is done, it's basically is going to, the same thing, like as I said, write it down to a CSV file at the bottom. And I realize that I'm going fast, but that's, just want you to get, get the main idea. So this Jupyter notebook is what we use basically to visualize that, let's say, 12,000 experiments, and how do you want to do that? And that's one good way to interpret the results. So before we get to this, so this is about, there are different processing on that CSV file, basically different analyses that I've done, nothing too advanced here. So we start with 12,000. I've just put some thresholds that on the error side and whatnot. I'm filtering out some experiments that basically are horrible. I'm coming down to like about 4,000 experiments here, and I'm visualizing those. So what this does is that if you look at this graph, on the left side is the error. So validation mean squared error. So basically, the lower is the better. So that is the section that we are interested in. And we have a coordinate basically for each parameter. Now I realize, now you see some colors. So we have a coordinate per parameter. So we had P, we had Q, we had solver, max iteration, train window size. These were in our grid search, the parameter that we used to grid search. So for each of them, each coordinate is basically the range of values that was set. And then what we're doing here is that we are saying, pick me the best experiments, basically the lowest errors. So you can actually slide this. These are the worst ones. But on this one, which are basically lowest errors, you can see that for the best experiments, for example, if I make it tighter, I'll see that p-value of 1 and 6 are basically coming up in the best experiments. And then q value of 2 are basically, again, the best experiments. On the solver side, which solver we use is more spread. So solvers, it's not that much of a differentiation here. Max iteration, the same. And train window size, they either go to 60 or to 180 days. So this is basically when you have a huge number of experiments. And it's not a good idea to sort this just by the error and pick up the top one, because somehow, most often, that top one could be kind of an anomaly that gave you the best result. But it's actually not from the best region of this multidimensional space. So that's one way to pick up the best experiment. Just to give you an idea also on how the prediction goes. So here, just a notebook, we give, let's say here, the best experiment for P, D, and Q. And we want to actually visualize the prediction. So it's going to trade here, and then it's going to make a prediction for each of those 30 days. And that is basically the predictions on the 30 days. So here we have a test set on the blue, and then the predictions on green, and then there are other metrics that actually ARIMA gives out, like standard error and confidence interval. We are also plotting that. So that is basically just to give you a visualization of how the prediction goes when you want to visualize it. So I intentionally actually went a bit fast so that I leave maybe a couple of minutes for questions if there are some. And before I switch to section 3, do we have questions right now? Just could you wait for a microphone, please? Sorry for that. But go ahead. I'll say it.
I just wanted to ask could you explain again the two different modes of single core and multi-core and how it was? So you said that if the package is actually using
I'll explain. I got the question. So some libraries, let's say, for example, TensorFlow itself. TensorFlow is using all the cores that you have on the machine. So you don't need to use Spark for spreading the execution on a single machine. TensorFlow is already going to max out all the cores on that machine. And that is falling in our multi-core flag that we have, that the library is multi-core already. So we have 2 clusters, but sometimes you can have actually a larger cluster. So a larger cluster of workers, and so that is the so there's a benefit definitely. If you have, let's say, a cluster of 20 workers, you can still 200 workers. You can still use that to use Spark to distribute it, but then within each machine, the library itself is going to do the multi-core usage. A single core is that a single library, many algorithms in scikit-learn, they are single core. So you would definitely want to go with the single core option flag, so that you use Spark not only to distribute it over the workers, but also within each worker over the cores of that machine. Any other questions?
Yes, please. Actually, I have twofold questions. So the first part of the question is, you mentioned at the beginning that you have two clusters with a number of cores and the memory. How did you come up with a way to size the cluster, or was it something just random that you decided?
The two. So this is our standard setup for the cluster for our platform, but it's not sized against any specific use case. We can do that if you want to. It's just that we have a permanent, let's say, 4 primary nodes that we have. Master 1, master 2, 1 CPU worker, 1 GPU worker. But then, if we have a use case, let's say if it's big data and we need more, then we have extended basically, and we have more workers to accommodate more data. But for this demo, I'm using a standard setup, our base setup,
Okay.
which is basically handling what I'm showing today.
Okay, thank you. Then the second part of the question is, the experiment seems to be quite fast. How big is the training data?
This is actually very small. This is the use case that I'm showing on the distributed grid search with a single core mode, and even actually the other one. This is using Spark to distribute the training when we have small data sets. So basically, here, the data set is about actually 700 days, so 700 records is a small data set. But it could be higher, it could go up to whatever the system RAM of a single machine can hold, basically. So up to that, you're good. But then if it goes higher, then you have to change how you want to do it. You want to switch to the big data.
Thank you very much.
I'll have a Q&A at the end too, so if you don't mind, I'll jump back and I'll take questions there at the end. The part that we have here is using Spark in a let's say traditional role, which is big data. Again, in this demo, I'm not going to do big data, but it is big data ready, let's say. That is, you're going to use the same code, and if you have 1 gig or you have 1 tera, that's the code that you can use and run. Basically, it's going to handle it. So I'll show you a Zeppelin node here, which does the training, and it does the model export with MLeap. And then there's a Jupyter notebook. It's just to show you how you serve it with MLeap. And the Jupyter notebook is just for documentation purposes. It's all shell commands that are running within Jupyter. It's just so that we capture the output so that it's easier to explain. But that is the second part that I'll show you. So back to our Zeppelin. So by the way, maybe I show you that this guy has already finished. So this guy is going to be. So all 6 tasks are completed, and it's about spread about 5 to 9 minutes on each task. So that is what I launched just a bit earlier on that Zeppelin that I was demoing. So this is another Zeppelin code. Again, I'm gonna just show you the main parts, just so that you get a sense. This is an adaptation of a Jupyter notebook, if I'm not mistaken, that was included with MLeap demo. MLeap is an engine to productionize Spark models. So we just adapted here just so that we run it here. So we are getting the data set. We are putting it on our HDFS. There are some jars for MLeap that you need to put in your setup basically so that you can run it. And then when you call those functions, it's basically going to add the model export functionality to PySpark. So this is, let's say, running this on the record. So we load the data from HDFS. This was the Airbnb.avro that I showed you a bit earlier on Hugh's side. So it reads it from HDFS, some simple count. So this is about 400,000 records. So as I said, it's not big data because we're going to go faster here, and the times that you see are all in the order of a couple of seconds when it executes, so it goes fast, but it's using the Spark API, so you might as well put 1 trillion records there and it's going to do the same. As long as you have this, your question, you have a large enough Spark cluster that can handle it, then you can run the same code there. So this is just some null value replacement and some statistics that this data set has. So this is some variables on the, so the prediction variable is the price of a listing, of an Airbnb listing. And there are some variables like, square feet of that, number of bedrooms, number of bathrooms. So these are some statistics on this data that they have calculated, and we've just basically put the code here and then show you some grouping, average price per state, max price per state, another grouping here. And then we start defining our machine learning pipeline. So there are continuous features, there are categorical features, continuous ones. So I think I don't need to explain this part. Dividing it between training and setting, testing here. For our pipeline, we put a scaler on our continuous variables, continuous features. For categorical features, we have a one-hot encoder for the categorical features, and we basically now put them all together in a pipeline. And this is basically training a linear regression model on top of it. So we put all the elements of this pipeline together. The training is done. And then at the bottom is just exporting that model to disk. So that is the function that we say, okay, put the file now on disk on this place, and then we push that file onto HDFS. So that is the steps. And in the Q&A, I can come back and explain more, but I just want to cover the whole workflow for you, and I think I did. Now, just give you an idea of what MLeap is and how you serve it. So this is a function, this is a notebook just to show you the steps. So it's all shell commands, as I said. You pull the MLeap serving, and you start that Docker container. You say there's some volume mapping so that we can point it to the model that we are going to put on disk. And there's basically we start running it, and we put the model, we grab it from our HDFS to this local machine, which is actually our CPU worker. So this Docker container is running there, but you can run it anywhere. Basically, it's a relatively low footprint. We run it on our CPU worker. So we are grabbing it basically from HDFS, and we were putting it in our local machine so that then the MLeap can run it, can see it. So this is a notebook to work with this MLeap serving basically as a client. So here it's sending the model to the server. This is basically loading the model into the server so it can serve. So basically giving a path to where it is, and it's going to be the API/model that is going to be basically accepting the model. What I'm showing you here is it's something they call leap frame, which is basically the format of the request when you want to talk to this server. So when you want to ask for a prediction request, you basically need to format in a way, and they call it leap frame. And what it looks like basically is this. So you say that you give the schema, you say all the variables, the data types, and then that is all the values for the data types that are higher here. So we are basically giving values to the features. We are asking for prediction from the server. That's how it goes. So that is sending now the request and printing what's coming back. So MLeap, it's basically not only gives out the result, but it also returns all those intermediate steps, doing one-hot encoding, scaling, returns everything basically to you, so that if you want, you can examine what is done, what the model has done. But the last record is actually your prediction variable, which is the price that you asked for. But it also returns everything that happened in that pipeline as well. Last step, just deleting the model from the server. And I think we did it. So I've got a couple more minutes for questions if you have. Do we have, can I get a minute? There's a microphone here. It's going to come to you.
Thank you, Masood. It's very interesting. I have questions more regarding the first part of the presentation. I want to know whether you looked at convergence rates for grid search in virtual, I suppose, in the context of comparing virtual core performance and physical core performance. Was there a difference? Also, I was wondering whether there was also a possibility that you tried to run research on GPUs. Did you have any experience with that?
Okay. So, sure. The first one, so Spark actually, when it sees vcores, it only sees vcores. So you cannot really actually, I'm not sure, maybe there's a flag, I haven't actually experimented to see that. Likely you cannot ask it to just send start one task per physical core. It actually automatically sees vcores. So that's why on this machine, on this worker, we have 4 physical cores, each one 2 threads, so 8 cores, and we gave 6 cores to Spark. So it is already using the vcores, and I'm not aware that you can set it that it does not do that, that it just works on physical cores. So I cannot, maybe it's a non-answer for this part. The GPU part is the, if you, let's say, I don't know if you want to do that, but let's say if you have a multi-core library, as I said, that is already using all the CPU cores, you could very well use a GPU, let's say something like TensorFlow, that is using GPU. So you could use this setup, but in the multi-core flag, so that on each worker, there's going to be just one processing task, and that task is going to consume all the GPU resources. That is how it can go. Maybe one last question. Do you want to? Okay, I answered that. That's good. Any other question? All right. Thanks very much.